Hey everyone, welcome back. Today we are going to talk about CPU scheduling, one of the most important topics in operating system. What is CPU scheduling? CPU scheduling is the process by which the operating system decides which process will get the CPU when multiple processes are ready to execute. The main goal is to maximize CPU utilization, minimize waiting time and turnaround time, ensure fairness among processes. CPU scheduling is applied to the ready queue in the OS where processes wait for CPU execution. See, what is CPU scheduling? CPU scheduling is the process where the operating system decides which process gets the CPU when multiple processes are ready to execute. Okay, and the main goals are simple: maximize CPU utilization, minimize waiting and turnaround time, and make sure all processes get a fair share of CPU time. This all scheduling happens in the ready queue where processes are waiting for their turn to run. Okay. For first is FCFS, first come first serve. Type non-primitive. How it works? The process that arrives first in the ready queue is executed first. Analogy like standing in a queue at a ticket counter. Whoever comes first gets served first. Advantages: simple to implement, fair for processes in terms of arrival order. Disadvantages: convoy effect. If a long process comes first, it delays all others. Poor average waiting time in some cases. See, FCFS, first come first serve. See, first we have FCFS, first come first serve. This one is very simple. The process that arrives first will be executed first. Think of it like a queue at a ticket counter. Whoever comes first gets served first. It's easy to implement and fair in terms of arrival order. But the downside is the convoy effect. If a long process comes first, everyone else has to wait. Then second is SJF, shortest job first. Type can be non-primitive or primitive. How it works? The process with the shortest CPU burst time is selected first. Non-primitive SJF. Once a process starts, it runs till completion. Example: if burst times are P1 equal to 6, P2 equal to 8, P3 equal to 7, P4 equal to 3, P4 executes first. Then primitive SJF. Okay, now SJF, shortest job first. See, here the process with the shortest CPU burst time is executed first. See, in non-primitive SJF, once a process starts, it runs until it's finished. Okay, and in primitive SJF, also called shortest remaining time first. If a new process arrives with a shorter burst time, the CPU will switch to that process. SJF gives the best average waiting time, but it needs an accurate prediction of burst time, and longer process might suffer from starvation. C. Third is priority scheduling. Type can be primitive or non-primitive. How it works? Each process is assigned a priority value. The CPU is given to the highest priority process. Example: if priorities are P1 equal to 3, P2 equal to 1, P3 equal to 4, P4 equal to 2, smaller number equal to higher priority. P2 executes first. Advantages: useful for real-time systems, flexibility in assigning importance to process. Disadvantages: starvation, low priority process may never get CPU. Solution: aging, gradually increasing priority of waiting processes. See, third is priority scheduling. Let's talk about priority scheduling. Every process has a priority value. The CPU is given to the process with the highest priority. It can be primitive or non-primitive. This is great for real-time systems. But low priority process might starve, and that's where a technique called aging comes in, which gradually increases their priority over time. Okay. Fourth, round robin RR. Type primitive. How it works: each process gets a fixed time slice quantum. After the quantum expires, the process goes to the back of the queue if not finished. Example: time quantum equal to 4 ms. Processes P1, P2, P3 executes in turns of 4 ms each. Advantages: fair, every process gets CPU time. Good for time sharing systems. Disadvantages: if quantum is too small, too many context switches overhead. If quantum is too large, behaves like a FCFS. Okay. For these, round robin RR, one of the most popular algorithms for time sharing systems is round robin. Okay. See here, every process gets a fixed time slice called a quantum. When the time is up, the process goes to the back of the queue if it's not finished. And it's fair for all processes. But if the quantum is too small, there are too many context switches. If it's too large, it starts behaving like FCFS. Then fifth, multi-level queue scheduling. Type combination of multiple scheduling algorithms. How it works: processes are divided into different queues based on their type or priority. Example: system processes, interactive processes, batch processes. Each queue has its own scheduling algorithm. Example: Q1 foreground round robin, Q2 background FCFS. Advantages: can handle process with different requirements, separates interactive and background jobs. Disadvantages: rigid, processes cannot move between queues unless multi-level feedback queue is used. See, multi-level queue scheduling. Okay, and finally we have multiple queue scheduling. Here processes are divided into different queues. For example, system processes, interactive processes, and batch processes. Okay, each queue can have its own scheduling algorithm, like round robin for the foreground queue and FCFS for the background queue. Okay, it's great for handling different types of processes, but it's also rigid. Processes usually can't move between queues unless we use a multi-level feedback queue. Okay, thank you.